So, what we have seen in our previous treatment of boundary layers, we were restricting ourselves to flat flow over a flat plate and when the flow was laminar. What we understood that it's the effect of the flat plate will become less and less, and at certain point inside the fluid after a certain depth, the flow becomes that equivalent to that of the free stream flow. So, if we have a flat plate and a fluid is approaching it with a constant velocity, which is also known as the approach velocity, then close to the solid layer the velocity will vary from the no slip condition, which is 0 velocity on the flat plate, to asymptotically it will merge smoothly to the flow outside of the thin layer, which is known as the boundary layer, in which the effect of viscous forces are important. So, beyond the thickness of the boundary layer, the velocity will remain constant. And for a flat flow over a flat plate, laminar flow over a flat plate, this velocity, the constant velocity beyond the boundary layer, which is known as the free stream velocity, the velocity which is free from the viscous effects, it is known as the free stream velocity. And for this special case of flow over a flat plate, the approach velocity and the free stream velocity, these two are going to be equal. Inside the thin boundary layer, the effect of viscous forces will be predominant. Now, close to the surface, the effect of viscous forces will be more, and as we move away from the flat solid plate, the effect of viscous forces will be progressively smaller, and beyond the boundary layer the flow can be treated as inviscid, where there would be no effect of viscosity, and therefore the velocity profile in the flow outside of the boundary layer can just resemble just a flat profile. So, approach velocity and the free stream velocity outside of the boundary layer for flow over a flat plate, they are equal. Inside the boundary layer, the flow is two dimensional. The effect of viscous forces are going to be important. Beyond it, the effect of viscous forces would not be applicable. So, truly speaking, Euler's equation, which is for an inviscid flow, is valid for the region outside of the boundary layer, whereas Navier-Stokes equation, which is for a viscous fluid, for equation of motion of a viscous fluid of constant mu and Newtonian fluid, the Navier-Stokes equation would be valid for flow inside the boundary layer. And we have already discussed the historical significance of the boundary layer concept and how does that help in correlating the theory and the experiments while designing the motion of ships in sea. The thickness of this boundary layer is arbitrarily defined as the point at which the velocity of the fluid is equal to 99% of the free stream velocity. So, it is very close to the free stream velocity, and the number is defined as the 99% of the free stream velocity. So, if we call small u as the velocity inside the boundary layer, which since the flow is two dimensional, this u is going to be a function both of x, where x is the actual direction or direction of flow, and y, where y is the distance from the vertical distance from the top plate. So, u inside the boundary layer is a function both of x and y, whereas outside of the boundary layer it's a constant. The small u is simply becomes equal to u infinity, u suffix infinity, where u infinity is the free stream velocity. So, how does this small u, the velocity inside the boundary layer, changes with distance from the solid plate is something which is of importance, and we will subsequently see why it is so. But by definition of the boundary layer thickness, small u divided by capital U, the local velocity inside the boundary layer and the free stream velocity outside of the boundary layer, the ratio of these two is equal to 0.99, which is known where the value of y, where this condition is reached, is called the boundary layer thickness or the disturbance thickness. Now, we can understand that since the velocity asymptotically merges with a constant velocity, the variation of velocity near the edge of the boundary layer is very small. So, a small change in, it is difficult to demarcate the exact location at which the velocity becomes 99% of free stream velocity. So, this definition, though it gives you a pictorial view of the thickness of the boundary layer, is difficult to obtain experimentally with sufficient accuracy. There is definitely therefore there is a need to define some thickness which, unlike the previous one, which is differential in nature, unlike the differential nature of boundary layer thickness, it would be an integral nature, and the integrand would be such that the integrand nearly vanishes at or near the edge of the boundary layer. So, we have in the previous class we have also seen two integral thicknesses defined in such a way that when expressed as a series, a summation of a series, the later terms, which are the terms that represent the region close to the edge of the boundary layer, their effect on the total summation is negligible. So, these two thicknesses are known as the momentum thickness and the displacement thickness. So, displacement thickness, when we talk in terms of the reduction in mass flow rate because of the presence of boundary layer, and momentum thickness when we talk in terms of the reduction in momentum of the actual mass that is flowing through the boundary layer. So, this is what we have done in our previous class. Now, we would like to see if it is possible to obtain an analytic solution or close to an analytic solution for flow inside a boundary layer. We understand that this is a complicated situation, because inside this region the velocity is a function of axial distance, the velocity is a function of distance from the vertical distance from the solid wall, the effect of viscosity is important, and therefore, the equation that we need to start with is equation of motion or the Navier-Stokes equation for two-dimensional flow inside the boundary layer. And that there are various terms which would lead to complicacy whenever we try to analytically obtain a solution for such a case. So, we would see that some of the approximations which are quite common in the treatment of boundary layer, collectively they are called as the boundary layer approximations. So, what are those approximations? The logical basis on which these approximations are made, and how they can simplify a very complicated problem to something which is tractable. So, we would start this class with the boundary layer approximations for laminar flow over a flat plate. And whenever there is a flow over a flat plate under laminar flow conditions, it's approximated as a zero pressure gradient flow. And if we assume the plate to be horizontal, there would be no effect of body forces. If you consider gravity is the only body force which is present. So, the Navier-Stokes equation that we are going to write will be for a situation which is zero pressure gradient, since it's flow over a flat plate, and it's a situation at which the effect of body forces are not present, are negligible. So, we are going to write the Navier-Stokes equation for flow inside a boundary layer, which would look something like this. We all know that from our treatment of Navier-Stokes equation, if we write the x component, and we are writing the x component since this is the principal direction of motion, plus Vy del Vx del y nu, which is nothing but mu by rho, the kinematic viscosity, del square Vx by del x square plus del square Vx by del y square. and there is, as I mentioned before, there would be no effect of there is no pressure gradient or body force term in this. Now, here we are going to make a quick mental calculation of the significance of each of these terms. Now, we are talking about a flow where the flow and this is the boundary layer, and here I have Vx, which as I understand is a function of both x and y, and for this boundary layer to grow I also have a Vy, which could also be a function of both x and y. But if we just analyze this, we can simply say that this Vx is going to be very large as compared to Vy. So, Vx, it is the principal direction, the component in the principal direction of motion must be higher, significantly higher than Vy. But the thickness, the boundary layer thickness at any point is delta, and we understand that this delta is a function of x. As x increases, delta keeps on increasing. However, the value of delta is quite small. It's the thickness of the boundary layer is generally small. So, the variation of Vx with x and variation of Vx with y, if we consider these two terms, Vx varies from 0 over here at the solid liquid interface to a value equal to u, where u is the free stream velocity. So, Vx changes from 0 to u over a small distance delta. So, therefore, del Vx del y is going to be quite large as compared to del Vx del x. Del Vx del x simply tells you the variation in velocity between these 2 points over a certain distance x. So, the reason, the analysis or the understanding here clearly tells us that this del Vx del y because of the small value of delta is going to be significant larger than del Vx del x, or in other words, the gradient in velocity in the vertical direction is going to be quite large as compared to the axial velocity gradient. So, as you see from here, since Vx is large as compared to Vy and del Vx del y is large in comparison to del Vx del x, the product of these two, we cannot make any judgment about which one is going to be significant. Okay. So, each term contains two terms, and the nature of the variation or the magnitude of these terms are such that you need to keep both of these terms in the Navier-Stokes equation. There is no way you can say that let us say the first term is significant, the second is not, and so on. So, therefore, you cannot make any judgment, and both the terms are to be kept into this equation. Now, when we come to this part over here, here we see that these are essentially telling me about the viscous transport in the x direction and viscous transport in the y direction, okay, gradient of viscous transport in y direction. And from our discussion over here, we understand that this term is going to predominate, and therefore, this is going to be quite large as compared to this term. So, the second term is going to remain in the Navier-Stokes equation, and the first term can simply be neglected. So, the final form of Navier-Stokes equation for flow for inside a boundary layer on a flat plate can be written as this. And whatever I have discussed so far in terms of the magnitudes, the relative magnitudes of these terms and their interrelation, they are collectively known as the boundary layer approximations or boundary layer assumptions. So, one has to solve this equation for flow inside a boundary layer with appropriate boundary conditions. And what we need is we need two conditions on y, and the two conditions on y are at y equal to 0, which is at this point. Your simply Vx due to no slip condition would be 0, and at y equals infinity, that means at a distance far from the wall, the Vx would simply be equal to u, where u is the free stream velocity. Okay. So, these are the two conditions what we can say, and the other condition, the initial condition is at x equals 0, Vx would simply be equals capital V, where capital V is the velocity, the approach velocity, and we understand for the special case of flow over a flat plate, this V would simply be equal to u. So, the three conditions that are needed to solve this equations are at y equals 0, no slip condition, at y equals infinity, at it far from the flat plate, the velocity is equal to the free stream velocity, and at the beginning at x equal to 0, the velocity for a flat plate is equal to the free stream velocity. So, this equation now has to be solved for using the following three boundary conditions. Now, whenever we come across such an equation, the equation was first solved by Blasius, and it is also known as the Blasius solution. What Blasius reasoned that the velocity profile, the dimensionless velocity profile should be similar for all values of x when plotted versus a non-dimensional distance from the wall. So, he has reasoned, it is only an assumption that Vx by u would be a function of eta, where eta is y by delta, y is the distance from the wall, delta is the boundary layer thickness at that point. So, the dimensionless velocity is going to be a function of dimensionless distance from the solid wall, which is logical, because if you think of the velocity, the dimensionless velocity profile, it is definitely going to be a function of distance from the solid wall. But since the velocity is non-dimensionalized, we need to non-dimensionalize the distance from the solid wall as well. So, the only dimension which is physically significant in a direction perpendicular to that of the flow has to be the distance, the thickness of the boundary layer. So, eta, which is the independent variable in this case, is defined as some sort of equal to y by delta, where delta is the dimensionless thickness. But if you go to my previous slide, where I have written down the equation to be solved for the case of flow inside the boundary layer, this is not the only equation, this I call as equation 2. This is not the only equation that needs to be solved. Whatever be the solution, that must also satisfy the equation of continuity, which being the equation of conservation of mass must always be satisfied. So, the two equations which are to be satisfied for describing flow inside a boundary layer, the first one being equation of continuity, conservation of mass, that has to be respected at all times, and the second one is the equation of motion, or the reduced form of equation of motion using the approximations that I have described, commonly known as the boundary layer approximations. So, I have two equations to deal with. Now, it is sometimes advisable that instead of using two equations, if I could reduce it to one equation, then it would probably be obviously it would be easier to handle. So, I need to do something such that, is it possible to do something such that these two equations would reduce to only one equation, such that I need to solve one equation instead of the two equations that I have right now. And the way to do that is to define something which would automatically ensure that the equation of continuity is satisfied. Okay. And the way to do that is to introduce the concept of stream function, which from your fluid mechanics you already know that the velocities, in this case the velocities in the x direction and in the y direction, can be expressed in terms of a stream function which describe the flow. And you also probably remembered that what are the properties of the stream function, like the distance between the stream functions essentially denote what is the volumetric flow rate between these two. Two stream functions can never cross each other, and the tangent to the stream line is essentially gives you the direction of the velocity at that specific point. But anyway, we know that velocities can be expressed in terms of stream function. So we understand that Vx by definition would be del psi by del y, where psi is the stream function. And Vy would be minus del psi by del x. So, if you look at these two definitions of Vx and Vy, and if you plug them into equation 1, what you would see is it is going to be del psi del x del y, and this one is going to be del psi del y del x. And psi being an exact differential, the order of the derivative is unimportant. So, therefore, the result of this would be equal to 0. So, since the order of the differentiation is unimportant, irrelevant for the case of an exact differential, so del psi by del x del y and del psi by del y del x are essentially equal, and since we have a minus in here, the equation of continuity automatically gets satisfied the moment we start to express Vx in terms of a stream function, Vx and Vy in terms of stream functions. So, now we do not have the equation of continuity anymore, it is automatically satisfied. So, we just have one equation to deal with, which is the equation of continuity, which is the equation of motion. So, bringing in the concept of stream function allows me to substantially reduce the complexity of the problem. The next, it is still a partial differential equation. Vx and Vy are functions of both x and y. X and y are the independent variables. So, is it possible somehow to club these two independent variables and define a new independent variable, which is a result of x and y in a certain form related to the new dimensionless variable, and then express Vx, Vy and psi in terms of the new variable. I will repeat this once again. What we see here is we are dealing with a partial differential equation in the form of equation of motion. It would be even simpler if we can revert this partial differential equation to an ordinary differential equation. And since Vx and Vy are functions of x and y, two independent variables, if I could club these two independent variables in a specific way such that I end up with only one independent variable, and Vx and Vy are now not functions of x and y, but functions of the new independent variable. So, now in that case I then have instead of a partial differential equation, I have an ordinary differential equation where Vx and Vy are functions of only one variable, which is some sort of a combination of the two independent variables x and y. So, the method of converting a partial differential equation to an ordinary differential equation by combining the independent variables in a specific way, obviously it is known as the method of combination of variables. So, we will see how method of combination of variables can give a solution to this specific problem. And for that, we would first, our aim is then to obtain a relation between x and y. So, I start with this equation again and try to see what's going to happen if I do an order of magnitude analysis of this equation near the boundary layer. So, what is going to happen near the boundary layer? I am going to make a judgment on that. Near the boundary layer, Vx is approximately going to be equal to u, y is essentially equal to delta, and since the velocity does not change, Vx does not change beyond the boundary layer, del Vx del x del Vx del y is going to be equal to 0. So, if this is the boundary layer, the Vx does not vary with y beyond the boundary layer. So, at the edge of the boundary layer, the variation in axial component of velocity with y is approximately equal to 0. So, if we see this, then what we are going to do is, I am going to write this equation, the approximate form of this equation is as u instead of Vx, u by x, which would be equal to this part is going to be approximately equal to 0, since I have written over here, and this is going to be equals nu, and then what I have u, and the value of y is going to be equal to delta. So, the relation that you get over here, the approximate relation that you are going to get based on an approximation, based on an order of magnitude analysis, a scaling parameter, what you would see is that delta square is going to be equal to nu times x by u, and your delta is simply going to be equal to or approximately equal to nu x by u. So, if I define my new dimensionless variable eta to be y by delta, as we have done before, this would simply be equals to y u by nu x. So, this is the combination variable that contains both y and x in a specific functional form, and the functional form is essentially y by root over x, and we have these two terms which come from an order of magnitude analysis of the equation near the boundary layer, at the edge of the boundary layer. So, approximately it gives me a form of delta in terms of x. Delta is the film thickness, which is only a function of x. Delta is the boundary layer thickness, which is only a function of x. So, it gives me delta as a function of x, and since the dimensionless distance is defined as y by delta, so it is of the form of this only. So, therefore, my equation, the equation that I have over here, the equation of motion, which is Vx del x plus Vy del Vx del y is equal to nu times del square Vx by del y square. This can now be handled first by introducing a stream function, and second is by invoking the method of combination of variables. And the stream function that we have defined is psi, and the combination variable that we have defined is eta equals y root over u by nu x. And since stream function, since I am going to make everything dimensionless, I am defining a dimensionless stream function which is f equals psi by root over nu x u. This dimensionless stream function is a function only of eta. So, next what is remaining is to convert the equation, the governing equation, in terms of the stream function and in terms of the new independent variable eta. So, instead of Vx, Vy as a function of x and y, I need to have f eta as a function only of eta. If I can do that, this gives rise to a PDE, but since f eta is a function only of eta, this will give rise to an ODE. So, in the next class I am going to just see how this transformation from PDE to ODE takes place, and that would allow us to solve this equation in a more meaningful way, in a more easy manner, also eliciting fundamental information about what happens at the edge and on the solid surface for flow inside a boundary layer.